Hey, well done in getting this far. This is Networks Part 5, and it's the last in the series, and it leads on to something called matrices. Have a look around the screen. Here's a network diagram over here, and here's another one. And what we're going to do is we're going to introduce a different way. Here it is here, a matrix and a rectangular array of numbers, and the plural is matrices, and these arrays of numbers can be used to summarize what's going on in networks. And here they are down here. I don't know whether you can see the connection. But my question for you is, why would you not want to just keep drawing network diagrams? Why might it be neater to use these matrix forms? Okay, and the clue to this is, well, you can use technology with the matrix form. Let's have a look in a minute and see what you think. And come down and let's have a look at this conversion here, interpreting information with matrices. Now, matrices are arrays of numbers, remember, and what we're going to say is it's better from a technology point of view in handling those networks, rather than you can't draw them on a computer very easily. It's easier to use this form. So what are we going to do? Well, we're going to summarize the connections here between these nodes, in other words, looking at all the edges and so on, or the arcs in the network diagram. We're going to summarize that in this matrix down here. So the way we set it up is from A to itself, no connections. A to B, one connection. See it there, over there. Okay, see how we're going to, if you like, encode the network connections into a matrix form. Okay, so these are called adjacency or connectivity matrices. When you take a diagram and you put it into the matrix form. What's this mean? C connected to, here we are, E. C connected to E is 3. Do we agree? Oh yes, there are 3 ways up here in which C is connected to E. Do you get it? Okay, so here's some interpretations, some Hayes and Harris publications here. One path from B to C, there it is, B to C, and 2 paths from E to B. Do you get the idea? Not a bad little system, is it? It's a coded system of networks. Okay, come down and let's start talking about undirected networks. In other words, you can go both ways along the edge. You don't have an arrow saying, let's take this diagram up here. You can phone from there to there, but you can't phone back. It's not that. It's a undirected network. Go either way along the edge. So here we are. We have 3 people live in different cities. They can communicate with each other by phone, fax, or email. And so we're going to draw that with this network diagram over here. So, which people have internet access? Well, let's have a look. This one and this one can be connected. So that's Con and Way. Which ones have fax machines? C and S, Con and Sam. Okay, and find the adjacency or connectivity matrix of this network. Well, we can say Con to Con, no, he's already there, there's no connection. Con to Sam, let's go up here. How many connections? There's fax and phone. Con to Way, yep, email and phone. So can you see, we're summarising all the ways these people are individually connected. Sam to Con will be the same because we can go backwards and forwards. Sam to Sam, none. Okay, he's already there. Sam to Way would be 1. Then Way to Con, 2. Same as Con to Way. So you're going to get a bit of a symmetry there. There's our matrix. Just the numbers. We don't usually leave the titles in there for the rows and the columns. So that's one of the rules here now. You've got to remember what the rows and columns mean. So this is how they're all connected. Are you getting the idea? Could get complicated if you forgot what the rows and columns mean. So don't forget that. Okay, so here we are. Something that we've just noticed about these matrices. They are symmetrical or symmetric about the leading diagonal, because if you looked over on this one, there's a leading diagonal from the top entry back down to the right. So this is, what was it? Sam and Con, and this was Con and Sam. So because they are not directed, you're going to have matching entries across the diagonal. Sam to Con or whatever, and so on. Okay, so it's going to work the same both ways across that diagonal. And here we've got it here, the same idea, because the network is undirected. You can go from this one to this one, or from this one back to this one, and it'll be the same. All right, now what about this leading diagonal? It's all got zeros. What's true about that? Well, that's because if A was connected to A, there's no ways. B connected to B, there's no ways. They're already there. It's connecting to yourself, if you like. Doesn't make sense. But hang on. Undirected networks, there may be an exception to that. Do you want to see what that exception is? Come on down and have a look. Here it is here. Of course, A, or let's do F for a start, because that's what we're just looking at. F could be looped. There could be a way of driving around and coming back on a road to F. So see here, the diagonal, here's our diagonal coming down here. All the others aren't connected to themselves, but vertex F is, because it's got a loop around it and go out and come back to it. So an entry in the diagonal means you have ways of going around and back to that point. It could be 1, 2 or 3 or something like that. Notice here, the other one over here, this isolated vertex. If a vertex is isolated, that means A to A would be nothing. A to B, C, D, get nothing. And also, going into A, B to A. So this column here would mean it's isolated both ways. You can't get out from A and you can't get into A. So just think about that one. All right, so here's the upshot of that. A row of 0 corresponds to an isolated vertex. A non-zero number on the diagonal shows a loop, because generally you can't go from C or D to D or whatever. Okay, oh, hang on, that's not on the, we want this one down here. Okay, you can't go from D to D unless it's looped with itself. All right, getting some rules now for this new system. It's interesting, it's a really exciting and big area of mathematics later on. So let's try and put this in to a connectivity or adjacency matrix. So we've got 6, A, B, C, D, E, F. So we're going to put it down here. We're going to leave these out eventually, because technically a matrix is an array. It's not got listings on the side. We have to remember that. So this is what we've got. Now let's do A to A is 0. There's no loop on A. A to B, one way. Yep. A to C around the outside, one way. A to D, one way. A to E, one way. A to F, no direct connection. Can you see how we build this matrix up? Then B to A, 1. B to B, none. B to C, none. B to D, none. B to E, yes, 1. B to F, none. So you've got to go and look at the vertex and see what it's connected with, because remember this is from here. So you start at this vertex and check out whether it has a direct connection or is adjacent to the other vertex. Okay, this is symmetrical because there's no loops, and all the other entries are 0 to 1 because each one is only connected once to any other ones. So you'll get the hang of this in a minute. Now, what I'm going to ask you to do is to have a look at this. This is a good use for adjacency or connectivity matrices, because you might say, are these two network diagrams equivalent? Well, if we went through and said A to B, C, D, E, and repeated the process, we would find that even though they look different, particularly with this out here, they do have the same connectivity or adjacency matrix. So they are topologically equivalent. In other words, they are each showing the same connections or the same number of connections to each of the vertices. All right, so that's a good use of the adjacency matrix, to make one up for two network diagrams and see if they are the same. All right, come on down and let's have some exercises for you. Here's question 1 from 7E1. Want you to try and do all of these, make up the matrix for each of them, and I'll take you down and show you the solutions in a minute. Let's have a look at question 2. We should be able to get, question 2, 3 and 4 we can get on there. You might have a go at a couple and then fast forward, make sure you're getting the right answers. Okay, let's go to 5. Oops, we should not show you the answers yet. Okay, check if the following networks are topologically equivalent. That is going to be comparing their matrices, because it's easier than trying to count up the connections and thinking about it that way, particularly for large network diagrams. Let's have a look at the answers now. Okay, that's question 1, part of question 2. 2, 3, 4 and part of 5 there. And then question 5. Okay, how did you go? Getting the hang of it? It's an interesting system, isn't it? It's encoding information into a matrix, and gee, this is an area of mathematics which is really important later on, of just how much information a matrix can contain. We'll have a look at that later in this presentation. All right, let's go down and develop it a bit. So what about directed networks, where you can only go one way? You might be able to go from A to B, but not back again. And then you might be able to go from A to C, but not back again. So you're going to have directions here. Okay, what would that be useful for? What would that be used for? Here we are. At a new ski field, there are 2 lifts to take the skiers from the kiosk to the A slope, and 3 lifts taking them from the kiosk to the B slope. One takes them from the A slope to the higher B slope. Okay, the skiers do not return to the kiosk using the lift because they ski back, so that's not a connection. Construct an adjacency matrix so you can see which way you can go more neatly, I suppose. So here we are, the kiosk, 2 to slope A, 3 to slope B, and 1 from A, the lower slope, up to the higher slope. So let's have a look at an adjacency or connectivity matrix. Kiosk to kiosk, none. Kiosk to A, 2. Kiosk to B, 3. A slope to kiosk, nothing going down, but 1 going from the A slope to the B slope because B is higher than A, and none coming back from the B to the kiosk or to A or to itself. So the adjacency matrix is this one. Okay, so let's have a look at its properties then. The last row contains only zeros. So what that means is there's no arcs leaving B. Okay, it's all coming in. Have a look at the diagram, all coming in. So we call that a sink. Everything going in, nothing coming out. It's sunk into that point. This first column is interesting. Contains zeros, because arcs only leave K. They only leave K, nothing coming in to K. So this is K from K, A and B. So nothing comes in to K, because K is where you start and you ski back. You don't have any arcs connecting it. So it's called a source. So if directed arcs only come out of a point or a node, they're called a source. That node's called a source. If arcs or edges only come into a node, it's called a sink. All right, so some new terminology. Can you see we're building up pretty rapidly with this idea of matrices? Here's 7E2, a couple of exercises for you there. Pause the presentation and see if you can answer the questions. I'll show you those answers now. Have a look. Okay, question 1 and 2. Okay, how are you going there? Let's build it up a bit more. Okay, it's exciting, isn't it, of how this is all going. And what we've got here is the last little bit for this presentation. Goes on for a little bit longer, but It's called further matrices. Could matrices be used for something other than summarising information on a network? Yeah, you've already used matrices. Little tables like this, because a matrix is an array of numbers. What's this as an array of numbers? 3, 1, 150, 2. It's a recipe. Okay. And what's this as an array of numbers? You can use square brackets. You've got to remember what all the entries stand for, though. Okay. So let's come down and see a few uses more broadly now, other than just networks. A matrix is a rectangular array of numbers arranged in rows and columns. Which of these three would you call arrays or matrices or a matrix? Have a look, just think about it. Is this a matrix? No, it's got entries missing and zeros wouldn't fit in there. But that's not a matrix. Is this a matrix? Yep, it's an array of numbers, all meaning some particular thing. Just remember, we're encoding information into an array, and we don't usually put the titles on the edges here. We don't usually do that. So it can be used as a for coding, actually, for encrypting messages you use in wars and things to encode information so people couldn't work out what was going on in ciphers, it's called. Ciphering. Okay, let's have a look down here, and that's how we usually put it. Just the array of numbers. So you've got to remember what is the meaning of each of the rows, here are the rows, and each of the columns. So we're developing a whole theory of matrices here, not just relating to networking. Okay, so let's have a look at pulling this apart now. As I've said, you have rows. We usually look at those first, going this way, and columns going this way. So this particular element here is row 3. You always say the row first, give it a location. The row first, it's row 3, and it's in column 2. So you could, if that was called the matrix A, this would be called the entry A32. Okay, you see there's a whole jargon and set of definitions that we're building up relating to how to refer to rectangular arrays. And then this one has 3 rows and 3 columns. So we call it a 3 row by 3 column square matrix. Same both way around. Length by breadth, it's the same if you like. So it's a rectangular array, and a square is a special example of a rectangle, isn't it? It's a rectangle with equal sides. All right, come down and have a go at some things here with our new definition. Here, what have we got? We've got 1, 2, 3, 4 rows and 1 column. We say this is a 4 by 1 column matrix. What's this one? Only 1 row and 4 columns. So this is a 1 by 4, always rows first matrix. What about something like this? If we had entries here and here, here and here, here and here, here and here, what would that be? Let's count them. 1, 2, 3, 4 rows by 2 columns. That's a 4 by 2 matrix. And we can enter these into calculators and on computers to handle working with them, unlike an absolute drawing of a network. Okay, we can reduce it. All right, so here we are. What's the summary? If we say it's an M by N matrix, the rows are M and the columns are N. It's M rows, N columns. And so when we say that, it's called the order or size of a matrix. So it's easier, what we're doing now is developing some words to make it easier to describe what sort of matrix we're looking at. Okay, let's come down and look at using some of that terminology. I'll hide the answers there. So can you write down the order or size of these matrices and find the particular elements? Okay, pause it and have a go. Here are the answers now. Just have them up there. Okay. So you might be starting to think with those football scores and things like that. There are a lot of things you can use matrices for. So let's start using them. Here's one here. Peter goes shopping at store A to buy 2 loaves of bread at $2.35 each, 4 litres of milk at $1.75, 1 500 gram tub of butter at $3.25. Write a row matrix for the quantities: bread, milk, butter. Represent the costs in a column matrix. Keep in the same order: bread, milk, butter. Later on we'll answer the question why they asked us to put one as a row matrix and one as a column matrix. And then if he goes to a different supermarket, store B, the prices are different, then let's do it. Bread, milk, butter. Store A, here it is. Easy to compare, isn't it? Store B is going to be cheaper. You can see here, because each of them is less. So it's a nice way of comparing stuff. Okay, come down and see if you can put some into matrix form for yourself. Question 3 and 4 here. This might give you an idea reading this. He bought 6 hammers, 3 pinch bars, 5 screwdrivers, 4 drill sets. Hey, what if he had several stores? Something like Bunnings or something like that, where you have a lot of items, different items here in store A and Adelaide or something, store B somewhere else. This would be a huge array of items and stores and make it very easy for the store or the company to handle their inventory or inventory. That's all the stuff that they're carrying. So can you get the idea? Matrices are very expandable. You can keep going, expandable, both directions, allowing you within a matrix to contain huge amounts of information. If they want to add up all they have in all their stores around Australia, handling it in matrix form could be done with technology. So it's an exciting area of maths. I hope you go on with it and study it a bit. All right, I want you to try question 3 and 4. I'm going to show you the answers in a minute. Here's question 5. Again, basically looking at summarising an inventory or an inventory, what stock you're holding or orders you've got, and that sort of thing. All right, come down and look at the answers. 3 and 4. I'll bring up the rest of 5 in a minute. There it is. Well, I hope you're excited about venturing into this new area of mathematics called matrices. It's a big and interesting area for future study, and I hope you will go on and study it later on. Now, that's the end of this course now on networks and matrices, so I hope to catch you in a later presentation. Cheers for now.